Good morning, everyone. So I'm glad to say I'm doing another HexCon talk. We're doing it slightly differently this year, meaning we're not getting beers afterwards. But I do have a pretty slick view of the ocean from here, so I'm not complaining too much. So what we're going to be looking at is code reuse and software that wasn't specifically made to be reused. So it's not an API, it's closed source, but we want to look at the functionality that this uses, right? So in the past, if we wanted to do this, we had to painstakingly reverse engineer the code, re-implement it in our own way, right? The alternative was we had to rip it out of where it was, including all of its dependencies, which is extremely time consuming. So a bit of an intro for what I do. I'm just some random security guy. I've dabbled in everything in InfoSec you can think of. I've done pen testing, red teaming. I do a lot of automation detection, a little bit of threat hunting, and product reviews as well, right? So I'll take different systems, hook them together, and automate away all the tedious parts of incident response. Every now and again, I get to play with some malware, which is easily my favorite part of it, but this doesn't happen nearly as often as I'd prefer. So what are we going to be doing, right? So most of the malware I see does the same thing over and over. It unpacks, decrypts, and ejects. So I'm guessing the reason for this is that malware that doesn't take the time to hide itself isn't going to make it upstream to where I'm going to catch it. It's going to get filtered out by mail servers. Antiviruses are going to catch it pretty quickly. So anything commodity, I'm not going to see. And then the things that I do see has a fair bit of work that went into it. So we have to dig into the PE file format if we actually want to work with these samples. So the PE file format has the .exe extension, which is what we all know it as, right? So unfortunately, there's no shortcuts here. We do have to know how this PE file format works for a lot of for incident response, malware analysis, and for what we're going to be doing today. So why do we need to know what this format looks like? So we have to find the malware, especially if it's been injected into another process, for example. We have to know what memory should and shouldn't look like. We want to be able to instantly spot from a memory dump what is malicious, right? Often we have to extract and rebuild it, so if something is injected into a process, we have to convert it back to an exe on disk. The reason we have to do this is it's incredibly hard to work on malware in a running state. The problem is we're going to rename functions, create comments, whatever the case may be, but as soon as that application stops running, all of this information disappears. So the Windows loader does a pretty good job at putting the executable in memory for us, right? The problem is if it's already there, we can't, or the Windows loader can't reverse it for us. And also we can do some pretty clever things if we know how this works. So specifically in this case, we're going to be looking at code reuse. So I have done some work in this in the past. 4 years ago in my HexCon talk, I released a tool called Cryptomnesia. So this tool took little pieces of malware, ripped them out of the original sample, and allowed you to mix and match afterwards. So you could create this Frankencode piece of malware that's specifically what I was aiming for, made attribution a lot harder. So for example, even though a threat actor has been known to use a specific piece of code, we now have malware that contains code from multiple threat actors. So it's not easy to know who actually created it. So the CIA did do some work in this. If you look at the Vault 7 leaks, which released a bunch of operational manuals from the CIA, they have looked at this, but it's not clear if they actually use it in practice. So instead of using code in this way maliciously, we're going to turn it around. We're going to take malicious code and use it for good, right? We want to minimize the reversing in this as much as possible. So the old approach was extremely time intensive, but especially during an incident, we are not going to have time to do it. So we want to minimize that. So how do we actually do it, right? The problem is the PE file format is extremely complex. It has probably upwards of 50 data structures, all doing different things. And we have to parse all of these, or at least all of the ones that are applicable to what we're doing. Unfortunately, there's no shortcuts, like I said earlier. So I initially put off learning how this works for quite a while. You're going to come back to it. There's no way that on this level, the malware you're looking at is not going to make use of these features, right? So like I said, incredibly complex, but we're going to skip through most of it and only look at the specific data structures we need. So we are lucky in that a lot of decent documentation is available for this file format. We've got nice little diagrams like these which make it easy to digest, as easy as it can be at least. So we're only going to be looking at 8 of these little blocks for what we're doing. And we're only going to slightly touch on what they actually do. So we're lucky in that there's a lot of tooling that helps us complete all of these analysis phases. We've got PE parsers that will show us specific fields in the exe, like time, date, stamps, checksums, whatever the case may be. So the popular one is CFF Explorer, which I'm going to be using. We've got PPEE, pronounced puppy, and P Insider. Those are the 3 big ones. When we want to figure out what the code actually does when we're reverse engineering it, we're going to need debuggers like IDA Pro, which is a commercial one, which I'm using. X64 Debug and WinDebug, these are both free and incredibly powerful tools. For quick prototyping, we're going to be using scripting languages like Python, and Python specifically has a library called PEfile. So what PEfile does, it allows us to extract information from an exe file in readable format, but it doesn't allow us to modify anything. In fact, modifying an exe after it's been compiled is extremely difficult. Any small change can mess up these data structures and it might not load, it might not function, or whatever the case may be. So this might be a bit of an information dump, but let's dig into it, right? So an exe starts with 2 bytes, MZ. So this stands for Mark Zabowski. He's one of the early Microsoft employees, and he is responsible for at least a part of this this file format and all the data structures it contains. So as a malware analyst, what you see fairly often is 4D5A, right, in hex. So these 2 bytes are the same as MZ, and whenever you see these bytes in a location you don't expect it, which is pretty much everywhere, you are virtually guaranteed that something malicious is going on. Similarly, you might see these 2 bytes base64 encoded, which is pretty common, and then it's TFQQ, right? So if we look at the DOS header, that's the first little stub in this. We only care about the MZ header and the last 4 bytes of the DOS stub, which tells us the location of the NT header. So you can see between these data structures, we've got this little program that says this program cannot be run in DOS mode. That is actually a 16-bit application. So if you run one of these executables in DOS, it's going to run that little code stub, and it doesn't execute the actual 32-bit or 64-bit code. After the little DOS stub, you can see there's a bunch of data. So Microsoft, for some reason, uses this as a convenient place to store additional stuff. Even though it's part of the 16-bit application, it doesn't get executed. The program executes before. So one example is the rich headers, which gives details about the specific compiler used. And you have things like delayed imports, which hardly ever gets used, but that gets chucked in there as well. So if we look at our second data structure, we've got the NT header. So the NT header contains 2 other data structures. We've got the file header and the optional header, right? So the file header includes a lot of exe specific fields. So it has an architecture entry, which tells us is it a 32-bit or 64-bit application, right? We've got our timestamp, when it was compiled, number of sections. So a section is a specific block of memory that contains some of these data structures. And then we've got characteristics. For example, is it an exe, is it a DLL, and loads of other things, right? So as a malware analyst, these fields are extremely useful, right? So a user is not going to see these fields. For example, if you right click on an exe, go to information and look at that info, right? It can tell you the version of the application and whatnot. This is actually in the manifest. So that is a text file in the resource section. So this information doesn't get showed to the user. The manifest information gets showed. So one nice example of this is when Stuxnet was first discovered in 2010. Researchers started looking at similar strains of the same implant, right? And one of the fields they were looking at is the timestamp field. That allowed them to create a timeline for exactly how Stuxnet progressed, how it was updated, and so forth, right? So when they published this information, the NSA caught on really quickly, and they blanked out this timestamp field. One mistake they made, though, is there's 2 additional timestamp fields in the exe. You've got the export directory and the resource directory. They both have timestamp fields, and they didn't blank these out. So researchers kept doing what they're doing, and they managed to link Stuxnet back all the way to 2006. So this was a major operation, right? Anything that goes on for 4 years has got some proper backing, and that was another indication that this was a nation-state attack. So as a malware analyst, a lot of these fields are going to be interesting to us, even though an end user might not see it. So if we look at our third data structure, we've got the optional header, which isn't optional, so the name is a bit misleading. But it has entries like the image base, which is where the application prefers to be loaded. The application entry points are the first commands that are going to be executed in the file. This is never at the beginning of the file, it's somewhere in the middle. We have our section alignment, which tells us on what memory boundary our sections are going to be aligned. Our file alignment, which does the same thing for data on disk. Checksums, which tells us if a file's been modified, and a lot of event file. I think there's about 50 of them or some such. So if we look at our next data structure, we've got our data directories. So these are entries that all link to other data structures, right? So if we have sections that are specifically for example, for resources, we've got our resource section, and then we have our resource directory entry. This tells the Windows loader where to go look for resource information. So resources are going to include images, pictures, icons, mouse pointers, whatever the case may be. So all of these data structures that are linked to are incredibly complex as well. So we're not going to dig into these. What we do care about specifically is the import and export directories. So firstly, we have to look at our section headers, right? So our section headers tell us where a specific block of memory is going to be. They all have their own permissions, and they're all used for different things. So by convention, for example, you have a .text section. This is where your code is stored. You've got .data, which is where your read-write data is stored, and loads of others. So this section tells us where this is placed in memory, how big it is in memory, where it's on disk, how big it is on disk, and all of the permissions associated with that section. So going back to our import directory, this is going to have a directory entry pointing to wherever it is. And what the Windows loader does with this is it tells it, or the application tells the Windows loader what functions it needs in other DLLs, what the DLL's name is, and the Windows loader will go fetch those and map it into our process for us. If we go look at our export directory, this is similar, just in reverse. So our application is going to tell the Windows loader we're exporting specific addresses, be it variables or functions, so other applications can use the code that we provide. So this is generally what DLLs do. There's no rule that says this has to be a DLL. You can have exports and EXEs as well. Though that is not standard, and your code has to be slightly different if this is what you're doing. So what happens in the export directory is you can have, let's say, 10 exports. So these are memory addresses that's going to be used by something. You can either reference these by name or by ordinal, which is just a number. So you've got 3 parallel arrays in this case. So let's say we have, in the last in the last array, we've got 5 entries. They all have a name. If we want to look at where these addresses are, we're going to take the specific index. So let's say index number 1, which is going to be some function name. We're going to look up that index in the address of names array, which is going to give us an ordinal number. We're going to look up that ordinal number in the address of functions, and that's going to give us the function address, which the Windows loader is going to use to actually map the name to the location for where it is on file, right? So lastly, looking at the loading process. So Windows is going to, or the Windows loader is going to pass all of these data structures for us, and it's going to map the exe into memory. So your memory alignment is normally 1000 hex, while your file alignment is 200 hex. So it's almost always the case that your executable on disk is going to be smaller than your executable in memory. So that is also one of the reasons why when we have a piece of malware, we can't just rip it out of memory. We have to understand how this file format works. We have to go read and encode it, so when we do run it for analysis, the Windows loader knows how to load it for us. What we also want to look at is the import address table. So I mentioned that the loader needs to know which functions and DLLs to load. And to give an example of this, let's say our program needs to use the internet function, so to fetch something from a website or whatever the case may be. It's going to have an entry that says, please load this specific DLL and give me access to these functions. The Windows loader is going to map those addresses back into our application, and our application doesn't have to know how this happened. It just has access to these functions automatically. The reverse is, if we expose specific functions, some application is going to do this process. The Windows loader is going to pass our code. It's going to look at the export directory, look at where these functions are, and map those addresses back into the process that requested access to it. And then also there's loads of other things going on. The loading process is extremely complex, but luckily for us, we don't actually have to look at how these work for now. So I know this is a lot of information to take in. I said we're also lucky in that we have tools that can do this for us. We've got great documentation for the most part, and we only have to look at a fraction of what these structures actually contain. You're going to be constantly looking up these fields, so you don't have to know them off by heart, and I end up looking at the documentation over and over when I'm working with these. So at this point, what do we know, right? What conclusion do we have? Is by looking at the data structures within these files, we can modify them to create exports. We can take a specific piece of code in malware and tell the Windows loader that we want to have access to this piece of code. So it's not going to run the entire thing. It's going to only run pieces of code when we want to use them. So there's a couple of reasons why we want to do it in this case. So one example is a lot of malware actually encrypts its configuration. So the standard for actually looking at these files, or the common approach, is to reverse engineer it and go create a decryptor as a malware analyst. So this is extremely time consuming. We want to make it easier, right? So we can, for example, create an export entry for the function that decrypts this information. We load this as a library, we call this function, and instantly we have the decrypted config without having to reverse engineer or recode this. Another example is I've seen malware that doesn't do a good job at its crypto implementation. So all it does is it actually decrypts and encrypts with the same key, but you have to, for example, pay a ransom before it will do it, right? What we can do is go hook or create export entries for the decrypt function, just call it ourselves, and the malware will decrypt our files without us actually having to pay a ransom for it. And then specifically what we're going to be looking is disrupting C2 channels. So if we have a piece of malware, we can see it's calling out to some site. We want to be able to disrupt this channel so that all the implants calling out to the sites can't actually be used by the attacker, and hopefully we can disrupt this server that they're using completely to make it unusable. So why do we actually want to take this approach, right? So the one problem we're having at the moment is that we have a lot of users working from home. They're not sitting behind a corporate firewall anymore, so where we could have previously just blocked something on a firewall, we no longer have that option. Another problem is that even when you identify malicious C2 hosts, hosting providers don't take them down, and this is a pretty big problem for us. So we've identified an attack. We know maybe some of our users are infected. We don't know how many, but we can't do anything about it. So I was thinking we can possibly do this by ourselves. So let's see if we can disrupt these channels without help from the hosting provider. So I did get a little bit of pushback when I started this research. Basically, it was an ethics debate on Hackback, right, which you've had back and forth a lot of times, especially on Twitter. So if you are being attacked, is it okay to attack back, right, to disrupt this channel? Generally, you're not allowed to mess with infrastructure you don't own, and in this case, we do not own this infrastructure, as I said. So you can also make the argument, if we do disrupt them, what are they going to do? Report us, right? So this is a victimless crime, but you still have people arguing back and forth. This is not a settled debate. So for this, I'm going to choose a easy or a common target, right? So what I'm going to be targeting is called Cobalt Strike. It's a commercial product. It's about 55,000 Rand per year for one license, and it is incredibly powerful. The problem with this tool is, although it's a commercial tool, a lot of APT actors are using it actively. So we've got, for example, the Lazarus Group, which is North Korea. We've got Charming Kitten, which is Iran, and they are known to use this framework quite extensively, even though the US doesn't export to these countries because of the Wassenaar Agreement. So presumably these licenses that they're using are cracked versions of the product, but the fact is they're still using these to attack us, so we do need to know actually how to defend ourselves against it. So Cobostrike has a large list of extremely powerful features. For example, you can do pivots to reach hard to get to targets. You can dump password hashes, grab screenshots, whatever you can think of. It's extremely extensive. What's especially nice about this tool is the customization we have over what our traffic looks like. So Cobostrike names this malleable C2, and it allows us to tailor our network traffic to what incident responders are going to expect to see. So for example, the screenshot is Cobostrike set up to make the C2 traffic look like an image that's being downloaded. As an incident responder, when you see this, you're not going to be concerned. It looks legitimate, where in fact it's how this implant is communicating with the command and control server. So this is incredibly complex, especially from a code perspective. If you want to interact with this server yourself, traditionally you would have to go reverse engineer all of this code, write your own parser, write your own generator. But we do not have time for this, right? Especially if we're in the middle of an incident, it's chaos. We have to figure out where we're exposed, if we're exposed, and we want to minimize this process as much as we can. So Cobalt Strike uses a reflective DLL, which has been modified to be position independent, right? So what this means is the author has the possibility of writing this implant in normal C, but it can still be injected into memory as position independent. We don't need the Windows loader to load this for us, which, as I said previously, when we're analyzing malware is a problem because we need it on disk. So all of the standard loaders that come with Cobalt Strike are injectors, so we can't just use it as is. So in this case, I needed to go create a simple wrapper for it, which allows us to run it from disk. It doesn't inject into a new section, and any comments we make, functions we rename, we can keep those and continue our analysis. In this case, because all of the configurations for Cobalt Strike are stored within the sample itself, we do need a valid sample of the implant that the attacker is using against us. So, going to the hard part, I said we don't want to reverse engineer this entire thing. Unfortunately, we do have to at least know how it works. So we don't have to know how it does something, only that it does something and what it's doing, right? So this is a screenshot of me debugging Cobalt Strike when I was creating this framework. So if you look at the second little block I highlighted, that's the function that initializes auto communication channels. So this didn't have a name in the beginning, I named it. And to identify what it was doing, I just looked at the code. It was calling a lot of internet function setup code, but it didn't actually do anything with it. So chances are this is just a setup function, and in our code we're going to need to call this before we do anything else, right? So what I did is I took all of these functions or variables and I gave them names. So this is a tool I created called PEpewpew, and it'll take a malicious implant, craft a new export directory for it, and give it the names that we specify. So luckily, to check into the C2 server, we don't need to reverse a lot of the application, and the existing code will do all the heavy lifting for us. So if you look at this, this is a screenshot of CFF Explorer, which I mentioned earlier, which is a PE file parser. This shows us the export directory for the implant that I modified. We now have access to all of these functions, which are the ones I named, and we can use this implant, which was traditionally a standalone application, as an API basically. We can create code that runs these functions even though the main implant is not going to be running. So this does all the heavy lifting. Instead of us having to go look at how the C2 functions work, we can just tell this implant, here's a piece of data, go send it off to the server. I don't care how you do it, just do it. So where we previously would have to code thousands of lines of code to mimic this behavior, I've done it in under 100 just by using the code that's already there. So there's a lot of ways we can actually disrupt these C2 channels. We can, for example, let's say we check in 100 malicious clients, 100 implants into a malicious server. A second, we're going to make this server completely unusable. I took a different approach. I decided I'm going to show some ASCII text. So the attacker, while they're using this framework, they first have to look at my pictures, and secondly, I'm going to make this server unusable for them. So even though our users might be exposed, they're still going to be infected. The server they're calling back to is going to be unusable. So because Cobalt Strike actually has a client limit, for one, we're going to stop additional beacons from calling back to the server, and hopefully we clutter the server's UI with so much information that it's not useful anymore for the systems that are infected and are successfully calling back to the server. So this brings us back to the debate. Should we actually do this, right? The problem is, if you think about it, what are we going to do instead? We've got infected hosts. We can't necessarily reach them. Some of the protection controls have been disabled by the users, which we see occasionally, and we have to protect the network from this threat. So luckily we've not been in this scenario, but I suspect I'll lean to one of these two when it does come to actually protecting the systems in these ways. So PEpewpew is a research project that I've actually implemented a bunch of different attacks into. So one of the other features, I'm not going to be showing these, but you can look at the source code, play with them yourselves. It's DLL proxying, sideloading, and hijacking. So what this does is it allows us to craft, for example, a DLL that's when it gets, or when the application, a valid application, requests the DLL from the Windows loader, our DLL is going to be loaded instead, and instead of returning or performing some operation like the application expects, we're going to do something else. One example of this is again Stuxnet. The Stuxnet hooked the DLLs that return telemetry from the centrifuges. So instead of the centrifuge saying something is wrong, which was the case, the DLL changed this message saying everything is in line, and when these devices started falling over and spinning themselves off their axis. The technicians looked at the analysis, the software said everything was fine, and they didn't actually know what the problem was. Another one I've implemented is just jumbling the import directories. So what a lot of antivirus engines do is they create a hash of the import entries. So they call it an imp hash. So if a malware author changes his code to look different to evade AVs, the input hash is not actually going to change because he didn't change the functionality. So AVs can now find multiple strains of the same malware just by looking at the import hash if they found one specific sample. So in this case, like I said before, the input address table is extremely difficult to modify, but it's possible to jumble some things around, which then changes the hash, which is what I did in this case. There's also some other features, like for example, changing the debug directories, which also causes antivirus engines to treat your sample differently. And my main research on this case has been basically how antivirus engines handle malware. So there's a lot of room for improvement. There's a lot of things it can do already, and you are more than welcome to go play with these, give me feedback. I'd love to implement some new features if you can think of them, and we can see where this project goes, right? So at least now we are in a position to perform these actions. We can possibly disrupt C2 channels. It's still up for debate if we should be doing this, but we have the option now. I'd love to take this project a bit further, speak to you guys about it. I'm going to be on Discord, so please look me up. We can chat about it, and we can see where the project goes. But I hope you enjoy the rest of your HexCon, and we'll probably look at this again in the future, so look out for it.